modeling and simulation for automation using MapleSim. So without further ado, let's get it started. So a brief outline of today's webinar. First, I'm going to give you an overview of our toolchain and how it is applicable to automation. Then I will talk about the engineering libraries in MapleSim. I will briefly touch on the CAD Toolbox and the apps. We're also going to review a few applications and model export and visualization, and also finally finish off with 2 examples. A little bit of introduction. MapleSim is our modeling and simulation tool that you can use to build a model of your machine. In addition, you do also have access to Maple with its embedded packages, which is quite handy for analyzing the model you've built. Finally, you're also able to export your MapleSim model and use it in your project or PLC. You can even visualize the exported model while you're running it in your tool. Something that I hope will be more clear to you after this webinar is the workflow of using MapleSim and how it will bring value to your toolchain. First, you will build a model of your system in MapleSim to act as a digital twin to your system. You can use your machine's CAD or even start from your machine's concept. After building the model, you would be able to analyze the performance of your machine. And this will give you valuable data that you can later use to reiterate over your design and also the model you've built. For example, you might find out there are some unexpected vibrations in your machine, and you would need to modify your design to help resolve this issue. Last but not least, you would be able to export your MapleSim model and deploy it in your automation project or your PLCs. So overall, you can see a workflow of building, analyzing, and deploying a model of your system. And who is this aimed for? Well, if you're a machine builder and you're exploring the design space for your new machine, or you have already built the machine, maybe it is even at the customer side, but you want to improve its performance or troubleshoot it, this toolchain would be very helpful, as we're going to see. But how do you build models in MapleSim? Here are some examples of the libraries in MapleSim that are relevant to automation. Each library has many components that can be used out of the box to model different parts of your system. For example, you can use bodies and linkages and joints from multibody to model the mechanical part. Add electric motors or power converters from the electrical library. Add hydraulic or pneumatic actuation using cylinders and valves. And if part of your machine has cables and pulleys, ropes and pulleys would be the go-to library. You can also build the model on top of your machine's CAD. So the idea is you import the CAD file into the MapleSim CAD Toolbox and define different machine components and their ports. CAD Toolbox then will export those components to MapleSim, where you would be able to use them in connection with other MapleSim components to build the model. The toolbox will also calculate the mass inertia properties for the machine components. This is quite important for the dynamics of your machine, say calculating the motor torque or forces at different joints. What happens after building the model? MapleSim includes many embedded apps that are great for doing quick analysis on your model. With 1D Motion Generation app, for example, you can generate a customized motion profile and apply it as an actuation to quickly find out how machine reacts to different inputs. Let's see another example of using apps. With Parameter Sweep, you can run the model through different iterations of parameter values to see how those values affect different aspects of the model. Say what the motor load would be if you change the cycle time or machine load parameter. So let's check out some applications of using MapleSim in automation. With the model built, you would be able to analyze the kinematics and dynamics of your machine. This will answer questions like how motion of one part will translate or correlate to the motion of another part, or What are the forces or moments on different joints for different payloads or joint friction values? Motor sizing. You can vary the payload or change the input motion and find out the motor load for the entire motion range, considering the whole machine dynamics. This will help investigate the motor requirements or whether or not there's going to be motor failure. A few slides earlier, I talked about the available apps in MapleSim, but something to keep in mind is that we can also work together or provide you with the know-how of building customized apps. These apps would be tailored to your application, and you would be able to do custom analysis by click of a button and share it with others as well. In this case of the Scutter robot, the customized app gets the motor torque values and plots it on top of the torque speed curve. We are going to see an example of a customized app later on when we are reviewing some examples in MapleSim. MapleSim is multi-domain. You can add hydraulics to work with the mechanical part of your machine. And by doing so, you can check the pressure values at different parts of the hydraulic circuit. Also, you can inspect the resultant motion for any unwanted vibrations. Every machine that moves and has compliance is prone to vibrations. And this can impact both the safety and performance of that machine. With MapleSim, you can simulate these vibrations and explore various options to resolve the problem. For this injection molding machine, for example, the compliance comes from the compressibility of the hydraulic fluid in the cylinders. Using this model, you can modify and test your control code to deal with these vibrations. This will finally result in reduced machine cycle time, increased throughput, and safe machine operation. This is another example of a multi-domain system, a rotary telehandler. The model includes the mechanical part for the chassis and outriggers and the flexible telescopic boom, as well as the hydraulic actuation. With this model, you can check the stability of the telehandler, the deflection of the boom, and the pressure at the hydraulic cylinders as the boom is extending. As done in this model, you can also work out the inverse kinematics, the code or function that will tell you how to actuate the platform cylinder to keep it leveled. The last application that I'm going to show is a cable robot. You can quickly build a model of a cable robot and analyze the dynamics, say the tension in the cables or pulley slippage. You can also derive the inverse kinematics for such a complex system. In this case, inverse kinematics calculates the actuation for each of the cables holding the box in the middle so that the box will achieve a predefined motion and orientation. With inverse kinematics taken care of, you can then focus on the design of the robot or check the motor or joint loads. Building and validating models take some effort. Good news is though, you can actually export a MapleSim model and use it in other tools. So the idea is you would encapsulate the machine model that you want to export as a subsystem with some inputs and some outputs. Inputs can be control commands to the actuators, and outputs can be sensor measurements. You can then export the model through FMI standard and use it in the tools that support this standard. I have actually provided a web page here that you can look up and find out the list of the tools that do support this standard. The exported model can become part of your project and can be run in the PLCs. By doing this, you can test your control code before hooking it up to the actual machine, run what-if scenarios, and check for any failures. Since MapleSim uses symbolic manipulation and code optimization, the exported model is fast. That makes it suitable for real-time applications as well. Not only you can add the exported model to your project, you can also visualize it. For the case of the B&R Automation Studio that has its own visualization tool, we export the model in a compatible way so that the same graphics that you would see in MapleSim will appear in the Scene Viewer window as well. We do also have our own in-house developed visualization tool called MapleSim Insight. You can load the exported model in Insight and run it. Also, whenever you run the exported model in another tool, Insight will show the visualization of that model. Example of this is shown in this video for Rockwell Studio 5000. In this example, a Logix Designer program is communicating with the exported model of an injection molding machine. You can see the visualization of the machine and some plots in Insight. See how it's helpful in getting visual clues of how changing a parameter, in this case a controller gain, can change the motion of that center platen. And this is the same thing that you can do in your tool with the model of your machine connected to your code. To recap, I talked about modeling and simulation in MapleSim, how to build a model of a machine and analyze dynamics of it, do component sizing, and see interactions of different domains. Any model you build in MapleSim is deployable in your automation tool. You would be able to test your control code and find out potential failures before commissioning the machine. This is the idea of virtually commissioning the machine. Keep in mind that at any of these steps, model building and deploying, we can work with you to demonstrate how our tool can bring value to your workflow, and we can help you achieve your goals in the shortest time. Okay, at this point, we can move on and review the examples that I've prepared. The first one is an example of a pick and place mechanism. We are also going to run a Telehandler model in Insight as well. So this is the MapleSim environment. You can see the list of the libraries that I talked about, a few of them that were relevant to automation on the left. So libraries such as multibody, hydraulics, and you can see each of these libraries are actually divided into some subcategories and so on. And this is canvas in middle is where that we do modeling. To get familiar with modeling in MapleSim and also get to know the CAD Toolbox, we're going to work on building a model of a pick and place mechanism. And for that, I'm going to start with the CAD for that machine. So I will click on the CAD Toolbox and select the file that has the CAD geometry of that machine and open it. This will open up the CAD Toolbox interface, and I'm going to use the CAD Toolbox to do a few things and later generate those components in MapleSim. Okay, so one thing that you might need to do in CAD Toolbox is you can see the different parts on the left for this machine, and you might want to group some of these parts together because they might represent a single rigid component in your machine. For example, I know that this base and this gear motor are rigidly connected together. So I would select this frame and gear motor and create a group based on these two parts and call it base. You can go ahead and do the grouping for other parts and components as well. Another thing that you would need to do in CAD Toolbox is to assign coordinates. And coordinates are the ways of defining motion between different components. And each of these coordinates is going to be a port on the generated component. For assigning coordinates, click on this Place Coordinate button. And here I will assign one coordinate here to be able to define a rotational motion between the crank arm and the gear motor. I will continue assigning coordinates in the other places of my model that I would need to do the same thing as well. And once I finish with the coordinate placement, then I can actually go ahead and hit on Accept and Return button. And this will generate CAD components and make them available in MapleSim. I have actually completed this process for this CAD geometry before, so I'm going to open up the model that includes those components. Okay, so these are the components that are generated by CAD Toolbox, and I'm going to use multi-body components to complete my model. Okay, so I will first fix this base to ground. So I'm gonna connect the ground port to a fixed frame, which represents an point in this space with the predefined position and orientation. So I'm gonna fix this base component. I'm also going to connect other components using appropriate joints. Connecting the port A of the base to the motor crank arm using a revolute joint. And whenever I click any component, you can see the parameters for that specific component showing up in the properties panel on the right. I'm going to leave them as default for this example for most cases, but you can modify these parameters in the way that makes sense to your application. Connecting the port B of the motor crank arm to the link 1Z. I'm going to copy and paste port C. And copy and paste. And we'll connect the port D of the link 1 all the way back to the port D of the base. And port E of the link to the suction plate assembly. The port F of the assembly and top slide is a bit different in a way that they should be connected using a prismatic joint. So I will connect those two using a prismatic. And for the prismatic axis, I'm gonna select the Z unit vector. Finally, in the revolute to from port G of the top slide to the base. I'm also going to provide a constant speed input for this first revolute joint, and for that I'm going to use 1D mechanical, rotational, and motion drivers, and I'm going to bring in a constant input. And I will provide about 100 RPM as the constant speed for this first revolute joint. I'm also going to attach a final rigid body to this pickup port to represent the mass that is being picked and placed. Again, multi-body, this time a rigid body. I can modify the mass and inertia properties, but I will leave them as default for this example. Finally, I will attach a probe to this revolute joint to be able to see a plot for the torque required to crank that arm. Okay, so at this point the model is complete. I can hit on this run button, and what's going to happen is that MapleSim will go through the model and find out all the differential algebraic equations that represent the model, and will integrate those equations forward in time and will show the results in the simulation results window. So now if I click on this play button, you would be able to see the 3D playback of the machine, as well as the real-time value for the required torque on the plot in the right. Let's go back to the model, and this time, instead of providing a constant speed input, what I'm going to do is to provide a predefined motion profile. And for doing that, I'm going to use motion generation app in MapleSim, and that will help us get more familiar with using apps in MapleSim in general and the motion generation app in particular. So I will go and open the 1D motion generation app. Once the app is loaded, I'm going to add two spans to the right and change the duration of each span. I'm going to go with 2 seconds for the first one, 6 for the one in the middle, and 2 for the last one again. I'm going to change the type of the motion as well to rotational velocity and change units to the ones I like. Here, I'm going to design my custom motion profile by interacting with app. I would like to speed profile to ramp up from 0 to 50 RPM during the first span and ramp down during the last one. Once I'm happy with the motion profile, I can change the name and click on this generate button, which will create a MapleSim component with this motion profile defined in it that I can use in my model. You can see this component is available for me under local components. I'm going to bring it to the canvas, remove the constant speed input, and replace it with my custom motion profile. Let's rerun the model to check the updated results. This time, I'm ramping up the speed for the first revolute joint, which is connecting the crank arm to the base. In the first 2 seconds of the simulation, the speed should be steady of the value 50 RPM in the middle, and finally it should ramp down. So once the simulation is finished, we can check the results. From the 3D playback, we can see how machine starts from standstill, operates at constant speed of 50 RPM in the middle, and in the end of the simulation, the speed goes to 0. And you can see how the custom profile changes the torque required for the crank arm as well. Okay, so up to this point, we built the model of pick and place mechanism using the CAD Toolbox and multi-body components. We provided a custom speed profile to the first revolute joint, and we saw the simulation results. Next, I want to discuss the idea of having custom apps in MapleSim, something that is tailored to your application, and you can do custom analysis by click of buttons and check some results. For that, I'm going to close this model and open up another version of the pick and place mechanism model. This is actually pretty similar to the one that we worked on together and built using the CAD Toolbox. There are a bunch of sensors attached to different joints to measure the force and moments on different joints. There is also logic for changing the mass that is attached to the this pickup arm, and there's this logic kind of changes the mass from mass load to 0 depending on which stroke that the machine is operating in the picking and placing that item. This model is also parameterized, so you can see 2 parameters in this parameter block. The mass load is representing the mass of the attached object, and cycle per minute defines how many cycles of picking and placing this machine would finish in a single minute. The interesting thing about this model is that there's already an attached worksheet to this model that you can think of as a custom-made app for running and analyzing this model. I'm going to double-click on this worksheet to open it up. The app is actually built in Maple, so this is the Maple environment. I'm gonna click on this button, and this will simulate the MapleSim model, but through this app interface. Okay, so the simulation is done. The app has ran the model and fetched the results, so I can expand this section. And you can think of this section as a customized result manager. You can browse different signal outputs, and you can plot that particular signal as well as some values for that signal, like the minimum, maximum, or root mean square value. In the next section, I'm going to programmatically find out how changing model parameters are going to change the model results. So I will expand this motor torque analysis section, and you can see the absolute value for the motor required torque is plotted here. There are some sliders and checkboxes for me to change and play with the value of those parameters. So whenever I change the value for either of these sliders, either mass load or CPM, which stands for cycle per minute again, I'm going to see the updated results. So let's just change the value of mass load and see how the torque results are changing, as well as CPM. One thing that I would like to mention here is that every time I change the value of one of these sliders, a full simulation is being done behind the scene with up to the 10 seconds, and results are getting updated. And you can see it is very fast, and that is mainly because Maple and MapleSim are using symbolic manipulation, code optimization, and code generation, and that makes changing the value and getting the updated results very fast and efficient. I can also uncheck these two checkboxes to give a range for these parameter values, and when I do that, you can see there's a minimum and maximum value for the mass load, and I'm choosing to have 11 different values in this range, and similar thing for the CPM value. And by doing that, I can now have a 3D plot of what's going to happen to my maximum required torque based on different values of CPM and mass load. And nothing surprising here. If you're moving heavier objects or you're operating faster, you would need higher torque for a machine to operate. Okay, and finally, you can export the data points and results from this worksheet. And this kind of shows how using Maple in combination with MapleSim can be useful in creating custom-defined app for doing analysis on your model. And this actually wraps up everything that I wanted to mention using this model. We started from the CAD for this machine, created the CAD components, built the model using multi-body components. We got familiar using MapleSim apps by using motion generation app to replace the speed profile with a custom one. Then I moved to this model and talked about the custom apps as well. Okay, so let's move on to the next example. That is a model of a telehandler machine, and I'm going to talk about code generation and using the generated model, exported model in Insight as well. So let me close this one and open the telehandler model. Okay, so first thing you would notice is that the model is organized in a subsystem called Telehandler with two inputs and some outputs. And this is one thing that you would need to do, organizing a model to have some inputs and outputs before generating your plant model, your machine model as an FMU. If I double click on this subsystem, you can see that it is multi-domain. There's hydraulic actuation circuit here. Let me just toggle off the labels a bit more clear layout. And you can see the chassis model, the flexible boom, and there's a platform on the end. The IK, the inverse kinematics for this model is also in place, so that the platform will stay leveled while the boom is raising or extending. In FMU generation, model export is going to happen through another app in MapleSim that's called FMU generation app, and that will be under FMI connector, FMU generation. So you would open up this app, and then you would select the subsystem that represents your plant model that you want to export. You would load it, check inputs, outputs, select those parameters that you would like to export with model, modify the export options if needed, and then finally generate FMU, and this will create a file on your file system with the .fmu extension, and that is going to be your exported model and will be something that you will use in your automation tool. I've generated the FMU of the Telehandler subsystem before. So what I'm going to do now is to open MapleSim Insight and run that FMU. And in the process, we're going to get more familiar with the insight and how it's going to bring value. Okay, close this one and open MapleSim Insight. So this is the Insight environment. I'm going to load the generated FMU. So you can see this Telehandler FMU. I'm going to open it. And, once it is loaded, you can see a 3D environment as well as the plot window. You can interact with this environment, change the settings. For example, here I will define that the Z-axis is the up axis, and I can configure my 3D view as well. And you can immediately see the 3D view of that telehandler on an uneven terrain. We're gonna change the some inputs, some parameters for this telehandler model, move it around and extend the boom and see how it's going to behave. Whenever that you're happy with these settings in Insight, you can save a session for Insight. So I've done this. I have a nice layout for the plots and the 3D. So I'm going to open up that session with the same FMU, and this is telehandler.sim data. And now that is getting loaded, I'm going to go to the Simulate COSIM FMU tab. There are some settings that you can configure. I will leave them as default for our demo here. First thing that I want to do is to run this FMU. So I'm going to click on this button and you can immediately see the signals for boom cylinder and platform cylinder force are changing. So now I'm going to expand this tunable parameters. You can see the list of parameters that you can change on the fly, move the machine around or raise or extend that boom. So let's change this speed actually to 3. And you can see that machine has started moving. Let's change this steering value as well to -30. I want to move the machine to this area here and extend the stabilizers, extend the boom, or raise it and see how it behaves. Okay, so give 10 again. I think it's good. We can stop it. Okay, so let me actually zoom in a little bit to have a better view here. Okay, so now I'm going to extend these outriggers. So, and for that, 1, and you can see they're actually extending. Let's put them down as well. And once they're in touch with the ground, I should be able to see the contact forces acting on those outriggers as well. Here we go. Okay, now what I'm going to do is to actually raise this boom, and for that I'm going to provide value here. So let's go with 1. Okay, and now also start extending that boom as well. 3 here. And you can see the boom extending. Again, everything is dynamic here. This is only the 3D view, but you can imagine that whenever I change a value here, actually that hydraulic circuit is providing the power and force for this cylinder or that extension for the boom to happen. You can see how that changes the forces here. So and IK is in place to keep this platform leveled as well. So everything, all the dynamics of the machine that you modeled in MapleSim is captured here in this format, in the FMU format here, and you can run it in Insight the same way that you would be able to run it in your automation tool as well. This actually wraps up the webinar. So thank you everyone for joining.